Can you hear me without the microphone? Because I prefer not to be tethered to this. In the way that our rovers are now free to roam over the surface instead of being tethered to a landed spacecraft. What I want to do today is to give you a brief history of our spacecraft exploration of Mars, and then talk about some of the latest results, including some just very recently from the Curiosity lander in Gale crater. So, if we could go to the next slide. We have many reasons for wanting to explore Mars. It's a planet whose climate appears to have changed dramatically from its early times to the recent times. We talk about possibilities that early on Mars was wetter, and we have lots of evidence for that now. And we think it might have been warmer, but we're not sure about that. It could have been a cold wet as opposed to a dry wet, and I'll explain why that's important a little more later. However, one of the reasons we are interested in where water is because water is one of the ingredients for life. And certainly Mars is a place where we are actively looking for signatures of past life and trying to find and define those environments where we might look for life today if it exists on the planet. We don't know. It's still a search in progress. We also look at the geological evolution of the planet. We want to understand the history of how planets evolved generally. That gives us insight into the evolution of our own planet, the evolution of how planets change over time, and the processes that work. Mars as a planet is smaller than the Earth, but its surface area is about the same as the land area of the Earth. The day is about the same, only 40 minutes longer, so Mars rotates just a bit more slowly than our own planet does. In fact, some of our missions try to work on Mars time, and that's hard, where your day is drifting by 40 minutes each day. And soon you're getting up when others are going to sleep. It's not fun. But that similarity in the rotation of the planet and the fact that its atmosphere is relatively clear, it's not like Venus or the outer planets of our solar system, giant balls of gas, that where the sunlight and the drivers for the weather and the processes there are coming from below rather than from above. Mars is more like Earth. Sunlight comes down, it heats the ground. That ground heats the atmosphere. We see weather, we see storms. We see sometimes vast dust storms that occur on the planet. And we'll touch on those in the talk here. So those are our motivations, but there's one more. And that one more is that Mars can be a destination. Of all the planets in our solar system, you can imagine astronauts walking and working, living on the surface of Mars. You're not going to do that on Venus, where the temperatures are hot enough to melt lead at the surface. You're not going to do that soon on the moons of the outer planets in their cold, icy environments. So Mars is that possible destination, and we do talk about the possibility of sending astronauts in the 2030s and beyond to the planet. But first, we need to understand what the environment will be that they will be dealing with. And that's what our robotic missions are doing today. If we go to the next one, please, Aaron. Okay, Mars exploration started a long time ago in the sense of when we first started looking at Mars with telescopes on the Earth, we thought we saw patterns that indicated that there were water pathways. This planet has seasons. Its rotation axis is tilted about the same as the Earth's, 25 degrees as opposed to 23 degrees for our own planet. And that means there are seasons on the planet. The polar caps come into the sunlight for periods of time, and then seasonally they go into periods of polar night as well. And when we looked at this, we could see things that we thought, because of the straightness of the canals and such, the artificiality of that perhaps that pointed to life on the planet. Now, in these days, at the turn of the last century, that was not an uncommon thing. We thought there might be people on Venus, on other places in the solar system, but since that time, we've learned a lot more. And in fact, even before we launched our first spacecraft to the planet, there was a lot of controversy that these canals actually existed, and the indications of life on the planet were really true. As we'll see in our next slide, when we sent our first spacecraft by Mars in the 60s, we got quite a shock. We were expecting something that was more Earth-like. This began to look like it was more Moon-like. There were craters on the surface, a heavily cratered surface, in fact. And we had a measurement that remotely could sense the pressure of the atmosphere. And instead of being maybe a tenth of our own, it was 100th of our own in terms of the surface pressure. So for that moment, Mars seemed to be a most moon-like planet and with very little prospects for life. Fortunately, we had another mission already in the queue, and as it flew out towards Mars, it showed that we hadn't seen everything with these early flybys. In fact, the early flyby only got about 20 images of good quality that it was able to send back in the time flying by the planet. Even in the later ones that flew by, Mariner 6 and 7 at the end of the decade, there were some mysteries. In the next time step, Aaron, if you'll go, you'll see a ring around a dark feature there in the middle, and we wondered what that was. You'll also notice in this picture something that we thought we did know about, which is Mars had polar caps. It had ice caps, just like the Earth did. Those ice caps grew during the winter, and they shrank during the spring and summer, just like we would expect from our own. So the fact that there was ice on the planet, that's what we expected. Now, let's go to the next time step. One other thing that our next mission, the Mariner 9 orbiter, which was the first spacecraft to orbit around another planet other than our own, it came in the middle of a great dust storm. This is a later global dust storm, so it wasn't a one-time occurrence for that spacecraft. And you're looking at the same side of the planet. It's just all the dark markings have disappeared underneath this dust pall that has raised a dust cloud that has covered the planet and has gone as high as 40 kilometers in the atmosphere there. And gradually, this clears out over about a 2-month period and goes back, and you see the normal view here, which shows the polar caps again, and also some ice clouds that formed. We call those the polar hood because they tend to be just stationary there over the caps during the spring seasons. And that's because there's water coming off of the ice caps, and it's condensing in the atmosphere. So even though it's a very thin atmosphere, and it's also very cold, we can condense clouds in it, and we know that from our observations. So let's go to the next time step. And here's one of those mysteries explained. That ring around there, that was the base of this giant volcano. The base of that would cover the state of Arizona. And the caldera is 25 kilometers high, higher than the surrounding plain. So this is a very massive object. And in fact, remember that dust storm? When they got into orbit and couldn't see the surface, they did see what they call spots. A north spot, a middle spot, south spot, and this spot. And those were the summits of these calderas that were so massive that they were extending above the dust haze that was otherwise obscuring the surface. Let's go on. We saw other things too. We saw landforms on the surface, including things like this, where you see these streamlined islands on the surface. And that meant that this wasn't moon-like. This was a planet that had water on its surface. And that was important. Now, suddenly, we were interested again in what we might find on Mars. On the next time step, we also saw these valley networks, what you would expect, just like on Earth. Here you got this branching network where the streams are coming together into bigger streams and eventually exiting too. However, you'll notice that it's not quite everywhere. That is, in the upper corner and the lower corner here, you don't see this. So this patchiness of the networks suggested that perhaps water didn't rain out of the atmosphere for extended periods of time, but maybe only in certain events, periodically throughout the history of the planet. But it did have water running on its surface. Next one, please. So the question was Mars once more like the Earth? Could it have had water running on its surface? The answer was yes, from the landforms that you just saw. Could it even have had an ocean? That one we're still debating about, but I'll tell you a bit more. So let's go to the next time step. That was enough for us to send a mission in the mid-70s, which was looking for life on the planet. And it was assuming that if life existed anywhere on the planet, you could find evidence for it everywhere on the planet. If you reach out and grab a sample of soil anywhere on the Earth, even in our driest deserts and such, you can find microbial activity in that material and such. So that was what this one set out to do. It had an arm, it reached out, it poked into the surface, it brought that soil sample back into the laboratories that were on the spacecraft, and it was looking for the signatures by looking for organic material, and it was looking to see if something would respire. It had some CO2 in a container. It was labeled so they would know how much of it would be taken up. If there were microbes that were assimilating that, or plants, or something like that, was taking that, trying to change it into something else, they would be able to see that effect. And there were other instruments that were also predicated on looking for life, as we know it, under the assumption that anywhere on Mars would have that. They didn't find organics. They didn't find any indication of life. That sort of stopped us because there's organic material on all the planets. It comes in meteorites and comets that bring that material to the surface. So where was that material on Mars? And then we begin to understand the consequences of a very thin atmosphere, mostly composed of carbon dioxide, 95% of it. And in such an atmosphere, ultraviolet radiation goes to the surface. There's ozone, but not very much, not like our own planet, where we have that protective layer in the stratosphere. So on Mars, the surface was essentially being irradiated, and carbon compounds in particular would be broken down. The evidence wasn't on the surface, but we didn't know where to look. And so we took a step back and we said, okay, maybe we're going about this in the wrong way. Maybe there are specialized areas on the planet, oases if you will, where we would have a better chance of finding the signatures, at least of that ancient life that was there when water was there. Today, if I were to pour water, liquid water, out onto the surface of Mars, it would either freeze, turn to ice, or it would boil away, sublime, into the atmosphere as a gas. It doesn't stay liquid because it's cold and the pressure is very low. So we look to this ancient time when obviously there was water on the surface and was looking for evidence of that ancient origin of life that tended to focus. So one way to do that was to say, well, where else is there water on the planet? And where is there water on the planet today? Because we do have water that's in the atmosphere, forms clouds, there is an ice cap. Although most of the ice cap during the wintertime is actually composed of carbon dioxide. The atmosphere is freezing out onto the polar caps. In fact, a quarter of the total atmosphere freezes out in a given winter in each of the poles. So that's a massive effect. We don't have anything like that on the Earth. Fortunately, I think. So let's go to the next one. Now with our new, more recent spacecraft in the late 90s and continuing into the early 2000s, the last decade of exploration here, what we've done is we've found a lot more about Mars. One of the things we found out is the topography of the planet. You'll see in the globe in the middle there, the colors there are indicating the elevation of the surface. The white areas are those tops of the big volcanoes. The red areas are relatively high. And you go through the yellows and the greens and then down to the lowest areas, which are there in blue. And you'll also notice a great rift across the planet. This is Valles Marineris, which, if it were on Earth, would stretch across the United States. It is of that length and such. It is a couple of kilometers deep. It's over 50 to 100 kilometers wide in some areas. So this isn't the Grand Canyon. This is more like the Red Sea and the Great Rift in Africa, or for us Californians, the Owens Valley on the Sierra Nevadas and such. So you can tell that if water were to flow downhill, where would it go? It would go to the blue areas. That's why they colored it that way, I think. So that is an indication of where we might look for the evidence of that. We have looked out there, but what we have found is that that blue area has been resurfaced by lava flows. In fact, the whole area has been resurfaced by lava flows. So that evidence is now buried beneath the surface. Let's, in the other charts here, you'll see a panel that is a Mercator map over here. So this is looking pole to pole, all the way around the planet. And you'll see a bunch of yellows and blues and reds there. And what that is the strength of remnant magnetism in the soil itself, in the rocks of the crust of the planet. And what that means is Mars once had a very strong magnetic field, but we've measured it today, and that field is very weak. And in fact, if you look at where that signature is being preserved, it's only being preserved in the oldest terrain on the planet. On the Earth, it's hard to find ancient rocks. We have plate tectonics. The surfaces are actually recycled. They're subducted down into the crust and recycled again. So it's hard to find an old rock. Mars has its old rocks still exposed at the surface. And this is telling us that there was a magnetic field long ago, but when those lavas covered the northern plains and when there were new impact craters that formed these giant basins of Hellas and Argyll over there, much more massive than just a single crater would be. These are thousands of kilometers across. When that was formed, that wiped out that signature and it wasn't re-imprinted, so the global magnetic field was gone. Now, why is that important? If we think there was water on Mars before, where's the water today? So let's go look for it. Next one, please. This is that topography map again. Next time step, Aaron. And this is pointing out some of the features. In the North Pole, we know there's this water ice cap. And you notice it has these entrance, these canyons that are sort of etched into the ice and built up over time. That's the spiral pattern that you see, and you also see a giant canyon that is cut into there, just about at the 9 o'clock position. In the south, it's much higher, because remember these are color-coded by the elevation given by the color bar there on the right. The South Pole is much higher, and it still has a thin cover of CO2 today. But it is very thin, and it is changing, even as we've watched it over the 20 years of space exploration at Mars. It could go away completely. And if it did, the water ice that was beneath it would go into the atmosphere, and it would be a much cloudier planet than it is today. So we're very interested into whether that's the trend or whether it's a cycle that will get colder and there will be more CO2 on that polar cap. So you see the lowlands and you see the southern hemisphere. And you notice the southern hemisphere is very heavily cratered. This was the part that our early spacecraft flew over. They didn't capture the big volcanoes or the low areas and such. On Mars, the way we date things, the way we say this is older than that, there are two ways. If it's beneath something, the thing that's beneath we say is older. If, excuse me, if it's in these very heavily cratered terrains, we say that's also older, because that's why they're more heavily cratered. The cratering rate is more or less constant. It has changed over time by our experience with the moon, the calibration of that. But this is the way we date the surfaces today. Next one. We see some pretty fantastic landscapes when we look around, but in some places we see this layering. Why is layering important? Because if I'm depositing things in layers, then I've got one kind of climate regime for a time, and then something changes, and I get a different one, so I form a layer. And in fact, you can see that there are steps, big steps in the layers, but there are also finer layers too. That's like looking at an ice core from Greenland or Antarctica and looking at the layers to tell us about the climate change over time. So that's what we want to explore. In fact, there's a series of layered terrains in Gale crater that Curiosity is now roving towards that we hope to be able to sample a good part of Mars history. Next one. So we've seen a lot of different aspects of the surface. Now, a warning. The one in the upper right there, that's pretty much natural color. The others have had the color stretched so that you can see some of the color variation, because that tells us about different kinds of minerals that are on the planet. And in particular, we're interested in things like carbonates, which should be there if there had been liquid water on the planet, and CO2 atmosphere. It should form the equivalent of the cliffs of Dover out there on Mars. Now, there are also places that look like this, for this is clearly a delta where the river has come in. It's slightly higher topography today because it brought in a lot of gravel and rubble, and that's more resistant to weathering than the softer terrains around it. But it is indeed a delta, implying that there was a sustained flow of water on the place. There are other kinds of clays, and gypsum is one of those, things that are formed in water, all indicating there was water in the surface. So I showed you the composition, the morphology, the shape of the surface. Those river valleys, for instance, indicated there had been water in the past. This does the same in terms of composition. Next one. In fact, you can kind of make a stratigraphy. That is, you can, if you were to drill down and take a core into the rock in some of these layered areas, what you would see are clay units on the bottom, surmounted by things that were alterations of basalt, and then a blocky unit that didn't have a distinct spectral signature of things that formed in water, which implies, again, that Mars was wet early in its history, but has since dried out. Next one. We've gone down to the surface and we've verified these things. We've done it in various ways. We talked about briefly the Viking spacecraft, which was a lander that set down and poked into the surface. It couldn't wander around into a different environment that was fixed to where it was. But after that, we decided the way to go is to have rovers on it. It started with the Sojourner rover, which was about this size. In fact, we'll show you a diagram comparing it to its successors here in a moment. We also landed 2 rovers on the planet. They landed on those platforms, and then we had to get them off the platform down onto the surface. And finally, we landed Curiosity. Curiosity has drilled into the ground, about several centimeters down into the ground, and it's taken that material, it's a powdering drill that pokes it up, grinds it up, and then you take that material and you put it into instruments on board the rover to do analyses of what's there. And we'll talk about that in a moment. Next one, please. Here's the comparison of our advancing technologies for the rovers in terms of their size and such. This thing out here is about 70 pounds. So imagine holding a lawnmower out at arm's length and trying to control it. There's a lot of stress on that. You'll note the systems that we use to rove over the planet. These big wheels and the rocker bogie kind of suspension so that they can climb over rocks if they need to. Next one. Here are some of the things that they see when they get up really close into it. Again, the colors are a bit stretched here to help. Most of Mars is covered by a very thin layer of dust. It's reddish in color. It makes all the places look kind of reddish when you look at it in natural color. But to see some of the mineral variations and such, we stretch the color to see it. For instance, you see these things that we call newberries, which are concretions that have been formed by water in material and such. And as the surface erodes away, they're left on the surface and they're just scattered all over in some of these areas. You'll also notice these veins that are through here. And when we analyze those, it shows that there were minerals that were formed as groundwater moved through the cracks in the surface here to the surface or drained away from lakes that may have been present on the surface. Next one. Here's a close-up of some of those, and you can see that boxwork structure, a sort of ridge that extends back there. The stuff in the veins is harder than the surrounding material, and so as it erodes away, it tends to show an elevated feature behind it. So what you're doing here, this scene is looking down from the rover, which has a camera that's about human height, looking down onto the surface. And those circles are where we actually tried to brush away the material so that we could get a good view, not of the dust that covers much of the surface, but of the basic rock itself. Next. And Gale crater, we also saw these kinds of things. See the rounded pebbles and such, and also things that look for all the world like they're concrete. That's a conglomeration of material that's been cemented, naturally in this case, by minerals that are activated in water and serve to glue the whole material together. By the size of the pebbles and such, you can estimate how much water was needed, how deep a stream needed to be to flow those rocks around and to produce that. And it's not a thin stream. It would have been waist deep or higher to move that kind of rock material to form the surface. So we know that there was water there. This is in Gale crater, which is an ancient crater. It's 4 billion years old is when the basic crater was formed, or the rocks that form it today were formed. However, we're going to see there's been some new results that suggested this whole scene was buried for billions of years and only recently exposed. that's good news, because remember I told you that the biosignatures that we were looking for are eaten away if they stay at the surface for very long periods of time. If I can bury them and then expose them for us to take a look at, now I know where to go look. Next one. Okay, change with time. We'll go through this just a little bit to try to give you a sense of, so here we are today, right up here, and then this is going back in time, and the numbers there are billions of years. We think Mars formed about the same time as the Earth did, about 4.5 billion years ago. We think the magnetic field went away very early. Volcanism, the activity that built those giant volcanoes, was also pretty early on, although it extended towards the present. We haven't seen today any sign of volcanic activity. We'd like to. We'd like to see some hot springs or other environments that would be the places where you go look for life today. So let's go on to the next step. If water was there once in the past because it formed those minerals, it shaped that surface, where did it go? And the next time step just tells you that there are two ideas of where it could go. It's either lost to space or it's still there on the planet, but it is frozen in the crust. Next one. We actually know there is ground ice in much of the planet. The blue areas in this map are the areas where one of our instruments has been able to detect ice in the top meter. We can do it remotely in orbit. One of the great things. To prove it, we actually landed something on the surface and dug down to the predicted depth to find ice. And as you'll see, we actually did find that. Next one. So, the Phoenix lander, which came and landed on the surface, when it came down, it's a fixed lander, and it had thrusters, and as it came down to the ground, it blew away all of the dust and debris that was above the ice on it. So what you see there in the white is indeed exposed water ice. And just to check that it really was what we thought, the next time step shows us we had a scoop on this one as well. It dug down through a few centimeters of soil, and we found water ice there. Now, since that time, we've kind of predicted where that water ice ought to be on the planet. In the previous slide, you saw that it went down to the mid-latitudes at least, towards the equator. It turns out that Viking Lander 2, which landed at 48 degrees north on Mars, that if it had been able to dig just a few centimeters more, probably would also have found water ice. And it would have been very interesting to sample that for biological evidence. Next one. Just to show you one of the ways that our various missions can help one another, the Phoenix lander that I just showed you safely on the surface, when they were looking at where they wanted to land, they had sort of picked box B. Next time step there. But they had only low resolution data from the Viking days, and they wondered what these sort of dark areas, these dark rings were and such. We got fortunately, we had another orbiter with a much better camera that came after them, and we're going to look at that square blown up next time step. And what you saw was a whole bunch of boulders on the surface. Not very good if you're trying to land a vehicle that's the same size as those boulders. Fortunately, next time step, we were able to find a place with very few rocks. And you'll also notice the kind of polygonal ground, very representative of what we expect in the polar regions of our own planet. Permafrost areas. Next. Now we have another way of looking for subsurface ice on the planet. Mars is still being battered today by meteors that come in and hit it. So is the Earth, but the Earth has a nice thick atmosphere. Mars doesn't. And so there are new craters that are formed on the surface. And in the blue triangles, it shows places where when those craters have hit Mars and have thrown material up, those are the ones that have icy bottoms. So that means that ice is very shallow there in the surface. These craters are typically a few meters across, and they excavate to depths of a couple of meters. So it's not very far away. Next one, please. This is the spacecraft that took those particular images and such. To give you an idea of the size of what we're flying around Mars today, that antenna that's at the top, that antenna is 10 feet across. So it's quite large, and it's returned over 200 terabits of science information from deep space. Now, that doesn't sound like much. Our phones are probably sending around terabits of information all the time, it seems like anymore. But this is from 150 million kilometers away, typically. Next time step. So the way we find the craters is we look for dark splotches by using a lower resolution camera, but it can cover much more area because it's not so high resolution. And when it sees a splotch, a new splotch, different from what we had seen before, we can zero in with the next time step, which shows a much bigger camera. This one has a mirror that's about 1/2 meter across. And that's the thing that enables us to see things that are as small as our landers and our rovers on the planet, even from an orbit that's 300 kilometers, 180 miles up. I like to think of that, I'm from California, and I like to think of that as you're seeing things that are about the size of a basketball in San Diego from Los Angeles. And that impresses me a bit. So what we're looking at here is that capability now flying today around Mars. Next. Here's one of those white bottom craters. You can sort of see the crater itself and the material that it was splashed out. And here the contrast is pretty true. That is, this stuff is really white, which means that ice is pretty pure. And it has been put down during a recent geologic epoch in which that ice has been put into the surface and it's now exposed. Next one. Let's go to the next one. What about the loss to space? Well, we've had a little bit of information about that, and we just launched this last November a mission that's going to look at this in particular. And the way it's going to do it is it's looking at the solar wind, which as it flows by Mars, remember, no magnetic field here, so there's nothing to divert the solar wind from interacting with the atmosphere. And it can strip things away. So you need to know the energies of both the neutral gas and also the charged particles that are flying into the planet. And we're going to look at the process today, understand how Mars might be losing mass even today, and then extrapolate that back into time when the sun was putting out less overall radiation, but much more ultraviolet radiation at the beginning of Mars history, to see if we can understand if that was enough to strip away the water very early on. Next. So, next time step, we talked about the ancient Mars, and we've spent a lot of time on that. Let's talk a little bit about recent Mars, which is the next time step. We're going to look at the last, say, 100 million years or so. Next one. The polar caps are a record of change in that period of time. And here you see the big canyon that cuts into it and the striations of that. This is the elevation of the ice. This thing is about 1.5 miles thick at its thickest part. At the base of it is what's seen over on the other side, and there were ancient canyons that have since been covered up by more ice deposition. Now, how did we see those? Next time step, please. What we can do is we can use radar to sort of take slices right through the planet. And as we do so, we send those radar beams down. They are reflected by layers that are in the ice cap, mainly layers of dust. So if there were no dust in the ice cap, they would pretty much just pass through and go to the bottom. They actually do that to some extent here. That's how we can see the underlying topography. Next time step. So what you see here are the reflections that we see by radar in the polar cap. And again, remember that we're looking through about 1 mile of ice in these cases. And what we're trying to do is to correlate these reflections, these bright areas where there's more dust and then less dust are the darker areas, to correlate those with the amount of sunlight that the polar cap gets. And it changes over time. I told you the rotation axes of Earth and Mars are about the same, 23, 24 degrees today. The Earth varies by as much as a degree or so, and those, we believe, are related to our own ice ages on the planet. Mars varies by up to 15 to 20 degrees, much more. It's a lumpier planet, and it's closer to Jupiter, which is sort of the big bully of the solar system when it comes to gravitational attraction. So these variations, which are millions of years in cycles, but with quieter cycles at hundreds of thousands of years, we think are the processes by which you build those layers. But it does mean that that polar cap is something that is younger than 10 million years. So that's a recent deposit on the surface of Mars. That's one place where water has collected. You notice that there's a time in Mars history where that whole thing tipped to a period where polar caps were more exposed to sunlight periodically, and that means that they probably weren't permanent caps at the end of summer that we know today. Next one. Well, here are some of the other aspects of Mars. We've talked about the icy bottom craters and such. We do catch things like winds coming off the polar caps, which bring material down. In fact, we've seen blocks of ice that have fallen from the edge of the ice cap down onto the surface. And we know they're ice because we look at them one time and then we come back a month later and they're gone. They've melted away into the atmosphere. There's also weather patterns that we can see and dust storms that you can see in there. There are gullies on the planet. We can map the temperatures of the planet. We can compare them to our models. We can look for other species in the atmosphere other than CO2, the trace gases that could tell us about activity, such as carbon monoxide. Next one. Dust storms, yes, we can see those. And here you see this very lumpy material here. That's in the atmosphere. And this is moving, and it's moving towards what was our Opportunity rover sitting on the surface at that time. That rover is solar powered. It has panels that are out there. They don't like having a lot of dust in the atmosphere because there's not much sunlight on your panels. And so this gave them a chance to go into a low power mode so that they didn't lose the spacecraft. So having this kind of knowledge kind of forecasts weather for another planet. Next one. One of our most interesting things that we've seen recently are, as you go through the Mars year, the temperature of the ground is changing quite a bit. The maximum temperatures that you get to can get up, in some cases, to maybe 20, 30 degrees below zero in these kinds of places, typically. There are a few spots where it can get up to above freezing. Well, at least it would right at the ground, but the temperature decreases very quickly. In fact, your toes may be okay, but your head will freeze, so you wouldn't want that. However, these dark streaks form only at the warmest times of year, and they extend down the slopes, and as they extend down the slopes, and then it begins to cool off, they fade away. And then the next year, at the warmest time of year again, they once again reappear, extend down the slopes, and then fade away in the colder times. The next time step shows another example of that, this time in color. And you can see, so each episode here is a Mars year apart, a Mars year being just a little less than two of our Earth years. In fact, I'm going to start using my age in Mars years, I think. But what does this indicate? The best analog for this, and we've seen such things in Antarctica, for instance, which are otherwise very dry, cold climate, we think it's a brine flow. We think it's liquid water on the planet. There's ice in the surface. It gets warm enough to melt just a little bit of that, and it flows then in the stream. It's not pure water because the temperatures are still too cold for that. But if I put salt in the water, I depress the freezing point of that water. So brine flows, meaning salty water, is our best explanation for this. And we're trying to understand where these things occur on the planet. Next time step, please. And here you see a distribution across the place, and including in the equatorial regions in that great rift and such. Next one. Let's talk a little bit about Gale Crater, which is where the Curiosity rover is. I told you that we've drilled into the rock and we've been able to analyze that material by looking at the potassium-argon isotopes and taking the ratios of those. You can get an age of the formation age of the rock. That rock cooled off, formed, in this case, 4 billion years ago. Now that makes sense because the crater density ages also say that's about the time that this landscape, how long it's been exposed to the atmosphere. We also saw that evidence for a stream bed, and you can see the markings of that indicated here by the blue. In fact, we believe there was a shallow lake that was down in this crater at one time. Let's go to the next time step. So here is the surface that Curiosity is roving over today. It visited this area a few months ago, And that's indicated by the round circles over there, or where they drilled into the crust to take that. But you notice that this is layered. There are rocks, see the white line following there is distinguishing between two layers above and below. And in fact, they drilled into the rock and they made the measurement of the formation time of the rock, but they also measured a couple of other things. Next one, please. So here's a picture of the drill holes themselves. One was a test hole where they were just working it out, and the next one went in and took the sample. As I said, it's a powdering drill, percussion drill, and so it makes a powder that you then dump inside the spacecraft to analyze. Next one, please. What did they find? They found a number of things. And the first is the minerals that were formed there had formed in neutral water. You may have heard a statement that you could have drank the water if you had been there when the water was there, meaning that it wasn't very acidic and such. There are sulfates in much of the soil of Mars, which indicates there are other environments that were more acidic. Those seem to have occurred later in time. So something changed on Mars over that period, and it may have been due to that early volcanic activity. The key chemical ingredients for life are present: carbon, hydrogen, nitrogen, oxygen, sulfur, phosphorus. Those are key building blocks for life as we know it today. Now, so what this says is that this site on Mars, at least in its early times, was a habitable site. It is a place where life could have originated. If it had originated, could have sustained itself. It doesn't mean that we know that it was inhabited, that life actually did occur there. So that's why we're still looking for the evidence of biosignatures, either formations in the rocks, like stromatolites, which are formed by biogenic activity, or organic materials that have long chains, which are representative of biotic activity as well. There was one other thing. There was an analysis of the argon, neon, and helium gases that were in there. And by doing that, they found that the exposure age of the surface was less than 100 million years. That's the cumulative exposure. Remember, the rocks are 4 billion years old, so this has only been exposed at the surface for a much shorter period of time. And that means it should preserve the biosignatures that we're looking for. The radiation won't have removed the organic material. So we're looking, but the place to look, next time step, please. The next time step is to look right where that layer is cutting down, rather than out on the flat where we did it, because we need to rove over here and take our samples over here, because that's the most recently exposed areas. But there must have been at least 3 meters of rock over this for much of the period that rock was down on the surface. That also implies there's a much more rapid variation of surface erosion on the planet. Next one. There's more to come. There are giant layers that are in this mound that's in the center of the crater, and the rover is working its way over there. Now, the rover doesn't move very fast. It goes about 40 to 100 meters a day, a football field sort of extent. We're limited mostly by our ability to see over the horizon. It's about this height. You can look out over the surface and see what's ahead of it. We don't like it to go too far beyond its view where it's operating only on its own reconnaissance. Next one. But we do know they're making tracks because we can actually see the tracks from orbit. If you can't quite find those in here, and the rover itself is in this picture as well, let me give you a little help. Next time step, please. So there you see the tracks with the arrows. They're about 3 meters apart, and that's actually the rover, and you can see the shadow of it as it stands above the surface there. Next one. This is a similar scene, and this is in color, and believe it or not, there are rover tracks across there. Take a look through the middle part here, and you'll see those. Next one, please. And we can go back and look at our past spacecraft, the ones that we've landed before, Pathfinder, the 2 rovers, the platforms, the Viking spacecraft. Next one, please. With the latest ones, we're able to capture them on their way to the surface. When they're being deployed and going into the atmosphere and the parachutes have come out, we've taken a picture of both the Phoenix lander in 2008 and most recently the Curiosity rover on its way to the surface. In this picture, this is the landing area, and you can kind of see these two bluish spots. That's where, as this thing was coming down and hovering, the rockets were thrusting down onto the surface and moving the dust away from that as it lowered the rover down on a tether. I'll show you a little video of that in just a moment. Next one. So here's our missions. I've talked about all of these. Next time step. There are 2 missions on their way to Mars, launched last November. The MAVEN mission, which will look at the escape processes that I told you about. India has also launched a spacecraft that will look at the upper atmosphere of the planet and image it. Next one. The Europeans have a trace gas orbiter that will go, and it will also put down a demonstration module that will live only for a few days on the surface. It's meant to demonstrate the landing for the next time step, where they'll put down their rover on a Russian platform that will become another station on the planet. And then finally, the U.S. is looking to refly the Curiosity kind of thing. Next time step, please. We kind of bounce it down here. This one is going to form a cache. It will drill into the rock, take as many as 30 samples of the surface, hopefully at different parts of the surface, so we got to find the right landing site that has that diversity in it. We'll put those things in the can, and then another mission will land on the planet, send out a fetch rover and pick that up, put it in the rocket, blast it off the surface of Mars back to Earth. And the reason for doing that is because the problem with putting your instruments on the craft that go to Mars is you have to put your hypothesis out there, and you can be wrong, and we often have been wrong, about exactly what you're going to see and expect. If you have the sample back on Earth, you can do an experiment, you can react to what you found or didn't find, and you can do more analysis of that. And not only one lab can do that, but all of the world's capability can be brought to bear. Next one. Well, this is pretty much, I like this picture, which is a picture of the Earth and Moon taken from Mars orbit. After all, we have cameras in Earth orbit that take pictures of Mars. Seemed only fair to reciprocate. But I also wanted to remind you that a lot of what we learn about the planets, it affects our perception of our own environment and our own planet back here. Mars, it shows that things can be right for life maybe, but it doesn't just automatically occur perhaps. And that's what we're trying to find out, is whether it ever did occur. That time when things were more beneficial to the origin of life, we think, on Mars, that's exactly the period when life also developed on the Earth, some 3.5 billion years ago. So, knowing that it did or did not, and if it did not, why it did not, would be important to us. Some people talk about human exploration and robotic exploration. It's all human exploration. The robots are just our extensions operating on the planet.